Welcome to the satellite communication course. We start with a noise figure. So noise figure is nothing but what? Input signal to the input noise power. Ratio of input signal power to the input noise power with respect to that output signal power to the output noise power. So we can write in terms of a temperature here, reference noise temperature here. So input noise power, that is K into T0B. Similarly, we have the reference noise temperature for the output. So that's why G K T0 plus Td, that is about a device noise temperature. So if you solve it, we'll get that equation noise figure is equal to T0 plus Td by T0 here, and then we can find out that noise figure, that will be equal to 1 plus Td by T0. That is about a noise figure. So this one is the noise figure. Generally, we consider that reference noise temperature is about a 290 K here. That is for the reference noise temperature. And these all the terms, that is just like a ratio with respect to the noise temperature here. Now then, we can go ahead to find out the G by T ratio. G by T ratio for our station. Now the G by T ratio means what? We have the gain and the what will be the, that will be the noise figure, or you can say that is about a noise temperature. That is about a G by T ratio. So that G by T is nothing but what? Whatever the system temperature for this system noise temperature for your receiver, and what will be the gain of your system there. So that is nothing but what? That is the ratio of what? A receiving gain of an antenna, because at a receiver we are calculating our station. So and then T is nothing but what will be the system noise temperature. So using this, that particular factor G by T is nothing but a figure of merit for the earth station. So to calculate that G by T ratio, we should know that what will be the received signal at the earth station. So we calculate that a received signal at the earth station, because of the gain at the RF amplifier, if you consider that is a G here, then the power received at the demodulator, because that will be nothing but a AIRP, that is PTGT, gain of a receiving antenna, and then gain because of the power demodulator input that at a G here, and that will be a path loss LP. Or we can write that is a PR into a G, because that is nothing but a gain of the receiver from the RF amplifier input to the demodulator input, from what? RF to demodulator input. That is about a gain. That is nothing but a G here. So in a satellite system, we generally consider that a transmitting power that will be EIRP is equal to PT GT. We just use the term. And then a modulation system or a modulation scheme, they are use either FM or a PSK there. And in that case, they are saying what will be the power transmitted, and that belongs to the what will be the carrier power, or we can say that same is nothing but the what will be the power received at the receiver there. So we can write in this particular equation C is equal to PR. So that's why the total noise power received at the demodulator, that is here we can say PR here in this particular equation, so that we can write the ratio for the carrier power to the noise power at the demodulator, and that will become say C by N is equal to, we have PR into G divided by the system noise temperature B into G, and that will be the power carrier power, and that power will be received at the demodulator. So that's why C by N is equal to PR into G, that is PR into G here we have written, and then KTS BG, that is about the total system temperature bandwidth. We have the G for the demodulator here. So that becomes what PR by K. We have a TS and a B here. Okay, that GG get cancelled. So PR by KTS into G here. So this one is about AC by N. But if you see what will be the equations for the PR, so PR is nothing but what, that will be the term for the transmitting gain, receiving gain of the antenna, and from that we can calculate that a PT GT, and that term if we write here for the receiving antenna. So this one PR is equal to what, a PT GT GR by LP. LP is nothing but what, a 4 pi R by lambda square. We say that a PR is equal to PT GT GR by LP. LP is nothing but what, a 4 pi R by lambda square. That is about a GR. So now in this equation, C by N is equal to PR by KTSV. And if you put that PR value here, so then we'll get that C by N is equal to PT GT GR by K TSP to lambda by 4 pi R bracket square. And that becomes a C by N ratio. Now we can rewrite the term again. This PTGT is nothing but a effective isotopic radiated power, and we have the term for the KB here. Then we have the another term, that is lambda by 4 pi R bracket square, and another that is about a gain of a receiver. Okay, this one, and we have the system noise temperature, gain of a receiver and a TS. So from this, if you see that a C by N ratio is nothing but what? It is function of what? What will be the gain of a receiver and the system noise temperature. Now here these all the terms are nothing but from the transmitting side. This one is the path loss, this one is about effective isotopic radiated power, and what will be the bandwidth and what will be the Boltzmann constant. But if you see that here, so C by N ratio is the only the function by the of the, that is the gain of the receiving antenna and the system noise temperature. Means that is the ratio is the of a ratio of the receive antenna gain to the system noise temperature. And that is this, or that particular term is called as a figure of merit. This particular term is called as a figure of merit. And that figure of merit for Earth station. This one is about a figure of merit for the Earth station. So we can say that generally we say that approximately that will be nothing but a GR by TS only. So all other factors are there. Generally we say that it is C by N ratio is depending upon this particular factor GR by TS. If that GR by TS term is increases, then C by N ratio is again increases. So all other factors are constant there, and so that's why we can say that if this term increases, then this will be increases here. If this term decreases, this term again decreases there. So we can eliminate that bandwidth term that be here, and we can write in terms of the total noise. We can write in terms of the total noise, that will be N is equal to what? B into N0, and N0 is nothing but what? A noise density, and that N0 is equal to, we can say it is about a KT here. Okay, N0 is nothing but a KT here. So in that case, we can write that C by N ratio, that will be C by N 0. Instead of N here, we will write C by N 0, because in term we are writing in terms of a noise density, C by N 0. And then we have the PTGT term, that is nothing but a EIRP, plus we have the term for the GR by TS. We have the term GR by TS if it is in a dB here, even if this one is in a dB. So this one is about a path loss equation. LP is path loss plus 2 to 8.6. Why this 2 to 8.6 terms comes? Because we have the Boltzmann constant term is there. This one we have the equation here. PTGT is nothing but, we can write that PTGT is nothing but what? EIRP. This term is nothing but a path loss. This term we have. So we have written the C by N is equal to EIRP, G by T here, then path loss term, and then we have the term for this. So we'll write here the 2 to 8.6 here. So now this LP, we say it is about a path loss. And along with that, one more term we have to add when we are writing the equation for the carrier to noise ratio, that is in a dB, and that will be the term for the Earth station. This one complete term is for the Earth station, and that is equal to what? EIRP plus we have the GR by T. This one is again a term, Okay, that will be for the, we say, a satellite here. So GR by TS we have, that will be again we say for the Earth station, and then we have the LP, we have a 2 to 8.6, and then we have the LM. Now this one is about the downlink, we can say. This one is about the Earth station. Now this term, this one we have written for Earth station means what? This one is nothing but for the downlink. Means satellite sends the signal, so that's why the EIRP for satellite, GR by TS is for the Earth station. This one is about path loss for the downlink here, and then this one is about a system. We can say that a system margin, LM, is nothing but system margin that is for the downlink here. So this one is about the equation for the downlink for the Earth station because of the satellite transmit. Okay, satellite transmit the signal PTGT by the satellite. Then GR, because the gain of a receiving antenna, because here the Earth station is receiving, so that's why GR by TS. Then path loss from the signal transmitting from the satellite to the Earth station. This one is about a downlink here. So downlink here. System margin from the downlink. So here the EIRP for the satellite, and here we have the Earth station. So that's why this is C by N ratio is for the downlink here. So this LP is refer here. We can consider LP and LM. That will be for the downlink. So similarly, we can write the equation for the C by N ratio. Same equation. I'll just modify here itself. In that, instead of that, we can write the C by N ratio. We'll write the C by N ratio. And this one is for the satellite. Okay, if you compare the equation, we'll write here this one is for the satellite. Then EIRP, EIRP, that will be for the Earth station. Then GR by TS, that will be for the satellite, minus LP, that will be the uplink, plus 2 to 8.6 minus LM, that will be again for the uplink. Okay, now if you see here, in this case we say that this one is about a carrier to noise ratio at Earth station. So in that case, satellite transmitting the signal, and then the gain of the receiving antenna, so that's by GR by TS. Then path loss, that is satellite sending the signal from the satellite to the Earth station, so that's why it is downlink. Fixed constant term. Then a system margin, that is for the downlink. But here in the case of C by N ratio for the satellite, EIRP for the Earth station means Earth station is transmitting the signal to the satellite. So satellite receiving the signal, so that's why the C by N ratio for the satellite. So in that case, that link will be uplink, and the satellite receiving the signal GR by TS here. So LP is for the uplink, satellite uplink here, path loss for the uplink, constant term, and this LM system margin, that will be for the uplink. So now both the equations are for the uplink and a downlink. Now if you consider the total satellite link model, okay, I'll just redraw the diagram. So in that case, this one is about the Earth station. Now you can see here, this one is the satellite transmitting the signal now. It has the solar panel. It is in a rectangular shape now. Okay. So now this one is about a satellite, we say. A satellite here. And it has a various antennas likewise. Just like we say single antenna is used for transmitting. So this one is about the uplink here. Another Earth station here. Now it will transmit the signal from the satellite to the Earth station. That will nothing but the downlink. So now in this case of a uplink, because Earth station transmitting the signal, so that here we are measuring a C by N, that will be for the uplink. This one is about downlink, means satellite transmitting the signal to the Earth station. So that's why the C by N 0, that will be for the downlink. Okay. So now C by N 0 at the downlink and C by N 0 for the uplink. So if you consider that a total satellite link, that will be nothing but a C by N 0, that will be a total now 1 raised to 1 here inverse here will write. So in that case it will be C by N 0 raised to minus 1, that will be for the uplink, plus C by N 0 raised to minus 1, that will be for the downlink. That will be the total equations here. Okay, C by N 0 for the uplink and C by N 0 for the downlink here. That is about a satellite equation. So now this one is about a total satellite link. We consider that uplink as well as a downlink, and then that will be the your satellite link design. And then for the given satellite link design, so what will be the a component for this system margin? What are the various components we are using at the transmitting side of our station and receiving side at the satellite, or at transmitting side from the satellite to the receiving at the Earth station there. So now we should know that a specification for the transmitter as well as the receiving for the Earth station as well as the satellite there. And then based on that, you can calculate that C by N ratio for the transmitting antenna and the receiving antenna, because the C by N ratio is depending upon that EIRP, effective isotopic radiated power, then your antenna efficiency, then again, then your path loss, and then your system margin. And this gives us the total satellite link or a total C by N ratio for the satellite. So we should know that for a given particular satellite, what will be the antenna we are using and what will be the operating frequency band. So operating frequency band, so for the uplink, if you consider that, then frequency is different, and then for the downlink again the frequency is different. So that's why we can calculate that for a given particular system. So see that ratio will be different because a frequency for the uplink and frequency for the downlink is different. So that's why the EIRP at the transmitting side will be different. Similarly, we calculate that A receive power. So again, we need to consider the frequency. So we need to consider the each and every factor. for the system margins and all. So that is about your satellite link. So in that case, we need to consider that a C by N ratio with a frequency reuse or a frequency with or without frequency reuse, and then you calculate that what will be the link budget for it. Consider that what will be the transmission equations that will be relating to the received power level at the receiver to the transmitted power, then antenna again at the transmitter and receiver. Then we have seen that path loss and other losses that will be encountered at the uplink and a downlink. Okay, that we have seen. Then we have seen that a power flux density, and that is nothing but a power density that will be received at a distance from the transmitter, and it will be depending upon that a distance, square of a distance. So power density will be reduces with respect to the distance, that is about a r here. Then we say that the gain of an antenna is depending upon a signal transmitted by the antenna and what will be the beam of that particular antenna based on the effective aperture area. So that's why we can calculate that gain of that antenna, and that is nothing but the ratio of the power received at a distance, because from that particular both side of an antenna or a beam we have to calculate to the power received at that particular point from the given isotropic antenna in a given region. So that's why 4 pi term again will come in the picture. Then we have seen that a noise, that noise is a function of the noise temperature. Okay, noise is a function of a noise temperature and the noise bandwidth. So that's why a term that will be a KT, and a noise power is nothing but a KTB here. Noise power is nothing but a KTB. And then we have obtained that a system noise temperature, and that will be depending upon that each and every stage in a given system, what will be the system noise temperature. And we calculate that system noise temperature for each and every stage and their noise temperature. And then we obtain that the ratio of the gain of an antenna to the noise temperature, that is nothing but a G by T ratio, or you can say that figure of merit of a receiver here that we have seen. That is about a G by T ratio that we have calculated. And then from that G by T ratio, we calculate that what will be the C by N ratio. G by T ratio we calculate. And we say that C by N will be increased when G by T will be increased. C by N will be decreased if G by T ratio will be decreased there. And that ratio of that gain of that antenna to the noise temperature, that is G by T, is nothing but the figure of merit of an Earth station. So that's why we say that a total C by N ratio for the uplink and a downlink we have calculated. That is a C by N ratio for the uplink as well as the C by N ratio for the downlink we have calculated. And that is nothing but a total link budget or a total link power.